Hello again. So let's slowly get this started again, and people will catch up along the way. So the next chapter was more of a continuation of the chapter about floating point sum benchmarking. So on a machine of mine, I measured that assuming we got a sufficiently large collection of floating point numbers, we ended up with a performance around 0.4 nanosecond per floating point element, which means that we are summing about 500 millions of floats per second. And that may sound like a lot. I mean, that's why basically people almost never need to care about performance when they are doing Excel spreadsheets. It's even bad floating point performance is still extreme performance in the eye of human computations. But obviously, when we know that we expect tens of billions of operations per second, and we get not even a billion, there's a problem here. There are actually multiple problems in this code, and the next chapters go over them one by one. One of our problems is that, sorry, that example was about squaring floats. No, I think actually that is wrong, and I should review it. Anyway, for summing, in any case, for squaring, the problem is that we create a new vector every time. I suspect that might be the reason why actually Matthew observed some unexpected performance. Probably I started writing this chapter by squaring, switched it to summing, and forgot to update it. Yeah, might be that. In any case, in any situation where in a loop you need to create vectors, you need to start thinking about memory allocation overhead. That's something that people can easily get overly obsessed about. So it's good to put a bit of a break here and tell people, okay, memory allocation costs about microseconds for typical allocators and allocation sizes. That's not a huge amount of overhead. You should not be hunting every allocation in your program. On the other hand, if in a tight loop that is supposed to run millions of iterations per second, you allocate data, that's wrong, and you should try to find a way without allocating that much. And so the way Rust allows us to avoid unnecessary allocations is through ownership and borrowing. So first, let's go a bit in the past and look at Rust predecessor C++. So both Rust and C++ use a pattern known as resource acquisition initialization, where the idea is that you have objects that represent resources like memory or open files. And when these objects go out of scope and they are automatically destroyed, you can schedule code to be executed so that the associated resource, the memory you allocated, the file you opened, is also liberated. And this allows you to automatically liberate the resource that your program allocates, which is a good thing because if you have one allocation function and one liberation function, experience from C shows us that people will always sooner or later forget to call the liberation function in one or more code paths, typically in the error handling code paths. And that will result in the program allocating more and more resources over time, which is not a good thing. So this in Rust and C++ is resolved using resource acquisition initialization and destructors. But the original version of this pattern in C++ did not address one common issue, which is the need to be able to move resources from one program scope to another. For example, when you return an std vector from a function in C++, which is the equivalent of vec in Rust, the fact that this did not result in the creation of a copy of the vector was reliant on sophisticated compiler optimizations, which only triggered in specific circumstances, and that generally made C++ performance harder to reason about. As a result, in C++11, the 2011 version of the C++ standard, the C++ committee tried to come up with a better fix after some pass-fail experiments, and the better fix was move semantic. And the idea of move semantic is as follows. You should be able to take the resource that one variable owns and transfer the ownership of this resource to a different variable. And when you do that, the original variable loses access to the resource and the new variable has access to it. And this can be applied in a very generalized fashion. It can be applied, it's automatically applied to function results. It can be applied when you need to send variables to a different thread and so on. The problem is when they designed this solution, the C++ standard committee over-engineered it a bit. One thing they did in particular, which had serious bad consequences, is that they made move semantics an opt-in feature that each and every user-defined type, class, struct had to individually add support for. And well, as you would expect, people did not do so in the existing C++ code bases because they would seem to work. It's just that where you should have move semantics, instead you got copies. And so these days, yeah, it's a bit of a joke, right? It's an experts-only feature that, well, it makes you feel good when you use it, but you are lucky if you ever see it working as advertised on anything than a toy example using only standard library types. So how did Rust address that? Well, Rust came the benefit of being first released 4 years after C++11, so they thought about the things that went wrong with C++ move semantics. The first thing that went wrong is that in C++, when you move resources away from a variable, that variable can still be used, but it's dangling, it's not pointing to a live resource anymore. And this amplifies a problem that has been in C++ forever called the null pointer, the reference problem, dangling pointer problem, but applied more generally to every resource. And this was already a problem before, and now that we have moved, it's become a more pressing problem, so we want to have some solution to that. That was one thing that Rust set out to do. The second problem is that people did not implement move constructors and assignment operators because that had to be done manually for every type and it was very boring. And what the Rust designers realized is that actually almost every use case of C++ move constructors and assignments could be covered by just making a bitwise memcopy of the original variable and then making sure that the original variable cannot be used and its destructor will not be run. And this idea that move could be just memcopy enabled move operators in Rust to be implemented automatically, which was a huge improvement over the need to manually implement it for every type. And finally, since move was just a memcopy, it means that for all types that did not manage resources, actually, if we are doing a memcopy, we might as well keep the original copy usable, right? So then we had in Rust a distinction between movable types, between copyable types, which do not manage resources, like arrays of floats. You can make a copy of an array, it's a bitwise copy, it does not affect the original array. And on the other side, we had types which could not be duplicated just via a bitwise copy, like types that manage files, memory allocations. And those implemented the true move semantics where the original value cannot be used after it's been moved. So this looks like this. Let's take vec, which is a type that manages a memory allocation and therefore is not copyable. If you have a vec that's defined like this, you are allowed to move the associated resource into a different variable. But after you've done that, you are not allowed to use the original vec anymore. For example, you cannot display it, and the compiler will report an error if you try to do it. In Rust, variables that have been moved from cannot be used anymore, and that's detected at compile time. And that works for other kinds of motion. For example, if you pass a vec by value to a function, then again, you cannot use it anymore. It's been moved into the function. The function acquired ownership of the associated memory allocation. For types that don't manage resources, like arrays, this is not true. You can make as many copies as you like, and you can still use the original values after making copies. In situations where you actually do want to create copies, then you need in Rust to ask for it using the clone trait, which has a clone method. And this ensures that you will not end up accidentally creating lots of copies of your big data sets all around your code, which was also a classic performance pitfall in C++. This is not always enough, however. We do not want, for example, to have situations where when we use a data set, we need to move it into the function, then the function needs to return it to us at the end, and then we need to take it back, put it back where it was, and start over. That would be much of a pain. And that's why Rust also has a mechanism to temporarily borrow own resources, which is called references and borrowing. So where do we start from here? Well, programming languages have been having pointers like C or mechanisms equivalent to pointers like Fortran array references forever. The problem is, as we've seen time and time again, pointers are a bit hard to use. If you give people fully generalized pointers where they can do anything, they can send pointers to data all over the code base, then you will get in trouble. Like people will try to dereference pointers that do not point to valid data anymore. They will try to compute new pointers from original pointers and get the arithmetic wrong, and then they will write into some random other memory. All sort of stuff can go bad. And so the way Rust addresses this is by proving at compile time a pair of rules that users must follow. First, if the code has access to a reference to some data and is allowed to use that reference, it means that the underlying data must still be alive. You may not have references to vectors that have been destroyed, for example. Second, when it comes to multi-threading, we observed that one good rule of thumb to avoid issues is that memory at any given point in time should either be shared in read-only mode or restricted to a single owner, but in possible with write access. So like reader-writer-lock semantics. It has been established in a multi-threading context, but then the Rust people realized that this applies in other contexts too. Like, for example, if you know about iterator invalidation bugs in C++, they are basically a single-threaded variant of the shared mutable access problem that multi-threaded programs suffer from. The problem here is that you're using an iterator over a dataset while modifying this dataset. And by modifying the dataset, you invalidate the iterator that was accessing it in read-only or read-write mode. And then the iterator points to random crap and bad stuff happens. So this results in Rust having two kinds of references, shared references and mutable references. Shared references are created using the ampersand operator, which if you have paid careful attention to my previous presentations, you've seen me use to create slices of vectors. So here I have a vector. I can create one reference to it. I can even have multiple shared references to it. They are copyable. And I can read from all of them. All of this is fine. Rust, however, does not allow me a few things that I would be allowed to do in C and C++. I cannot return references to local variables from a function. That's illegal in Rust because what actually happens at execution time in this case is undefined behavior, as I'm effectively returning a pointer to stack allocated memory that does not exist anymore once the function returns. And one rule that is more specific to Rust is that once a reference to data has been created, we do not allow you to override the data and keep using the reference after that. As soon as you start overwriting the data, you invalidate the reference. And this is what prevents iterator invalidation bugs and multithreading bugs in Rust. But how do you hand over temporary write access to your variables then? Well, using a different kind of references called mutable references. And the way these work is they kind of acquire an exclusive lock on the data. As long as this Rx reference exists, I can use it to read or write the X variable that it targets, but I cannot modify the X value anymore using X equal 2, for example, without invalidating the Rx reference. I cannot create more read-only references. As soon as I create my mutable reference, I invalidate all existing read-only references. And this allows us to get away from all the issues of shared mutability that you get in other languages. Just to give an example from Python to show that this is not just about C, C++, Rust, and Fortran. One very, very common mistake when using NumPy in Python is to do this. So you start by using NumPy, you create a NumPy array, then you create what you think of as a copy of a NumPy array, then you forget about it, and much later in your program, you start changing what you think of as a copy to use it for someone else because variable reuse is cool, and then you realize that the rest of the program starts misbehaving because you've accidentally changed the value of an A variable on the other side of the program that does something completely different. This sort of bug where one part of the program has a spooky action at a distance on a completely remote part of the program is a typical result of what happens when you apply shared mutability too indiscriminately in a programming language. So what do we get by having these rules in Rust? Well, we avoid many C and C++ pointer usage error that would all result in undefined behavior. We avoid issues pertaining to null pointers. There's no way in safe code to create null references. We avoid issues related to dangling pointers. As you've seen, the compiler proves that you will not access a reference after the original data has gone out of scope. We prove that you do not have misaligned pointers. You cannot just create pointers out of nowhere without unsafe code. We prove that there is no iterator invalidation bug because you cannot modify data structure when you're iterating over it due to the shared XOR mutable principle. And we prove that there is no data race between concurrently executing threads because, again, we prevent you from sending mutable references to your data to other threads and then keep using the data. And we get one more thing from this. Beyond avoidance of undefined behavior, we get performance. You may have heard, if you've been doing too much C and C++, about the restrict keyword, which you need to apply to all of your pointers in order to get good compiler optimizations on functions that manipulate at least 2 arrays. This keyword does not exist in Rust, and the reason why it doesn't is that every Rust reference, almost every Rust reference, has semantics analogous to this, because What the restrict keywords effectively says is the rule that every Rust reference implements by default. Another reason why we get performance by writing code that follows this model is that if you look at how CPUs actually work on the inside, they actually, CPU caches apply a variant of the same rule. Basically, when you have multiple cores that want to have in cache copies of the same data, the way they achieve this is by using something called the messy coherence protocol or some more evolved variant of it like MOESE and so on. And the way this protocol works is that at any given point in time, either one CPU has write access to a piece of data or multiple CPUs have read-only access. And what this means is that by following the Rust reference rules, naturally, you write code that is efficiently manipulated by CPU caches in multi-core CPUs, because you intrinsically easily avoid the scenario where multiple cores end up working on the same data with mutable access. Of course, there's a price to pay for this. This design is, to my knowledge, relatively new to Rust. Few other programming languages have tried this design direction before. Many languages try to avoid having mutation at all. That's the whole functional programming line of programming language design. Many programming languages try to avoid having shared access to data. That's the whole communicating sequential process family. It got a bit less popular, but these days Go is a popular example. But few languages realize, like Rust, that actually a variable could switch between a read-only sharing state and a mutable exclusive access state without any problems. And this means that things like GUI will be a bit more difficult in Rust, because you will be trying to manipulate code that's written for programming languages that have different reference rules where shared mutability is not restricted, as it is in Rust. Another consequence is that many traits in the Rust standard library and elsewhere end up having to exist in multiple versions, because sometimes you may want to manipulate read-only references, sometimes you want to use mutable references, and sometimes you want to use own values. One example of this is the fn trait that is used to define callable functions. It actually has two cousins called fn-mute and fn-once. So how does that work? When your function asks for an implementation of the fn traits, then it can call the function indiscriminately. It can call the function given only a read-only reference to it. But this means that it cannot accept functions that have some internal state that will be mutated every time the function is called. So here we have an option that's maximally flexible for the implementation of callFN, but maximally inflexible for the caller of callFN. If now we ask for fn-mute, then to call the function, we need a mutable reference to it, which is restrictive. But on balance, what we get is that now we can pass functions that mutate internal state on every call. And finally, we get the fn-once state, where if we accept a function that implements this trait, then we are only allowed to call this function once. But what this allows us to do is to call functions that can only be legally called once. And here I give you an example of a function of a closure that, when called, returns a vec object. So it transfers ownership of that vec object. It can only return it once. If you try to call it again, it would be trying to return, to move ownership of a resource that does not exist anymore. So that would not be okay. So with this, we have an option which is maximally flexible on the caller side. I can call this function with every possible function closure in Rust, But on the implementation side, I can only use this function in very restrictive ways. There's more to this, but we won't have time to study it in this course. So let's move on to how references interact with function parameters. There are a few easy cases first. Some functions only accept references to inputs and do not emit any outputs. This is not a problem. The Rust compiler proves that these references will be valid for the whole duration for which the function is called. And therefore, well, we just write these functions normally and don't care. Other functions take one reference to some data as input and return one or more references as outputs. In this case, the compiler will make an assumption. It will assume that all the references that the function return must come from the input reference. This may not be the case. You might want to return references to global data, for example, but that's considered an edge case. So when you want to do this, you need to specify it in the function signature. And finally, there is one third easy case, which is that if your function returns references that come out of nowhere, there is no matching input reference parameter. And then this likely means that you're trying to do something silly along these lines. So by default, the compiler will reject a function that has this sort of signature. If you do want to return a reference to global data, for example, again, you need to spell it out. And the compiler will check that indeed the data to which you're returning a reference has global scope. And so let's look at what the syntax looks like. So if you take references as input, well, you can just say, okay, I'm taking a parameter x, which is a reference to some type, let's say I32, and I can return references to that. If you want to return references to global state, you specify it using this little single tick. We'll get into what it means in a second, followed by the static keyword. So this means you're returning a reference to a variable with static storage duration, which you can use for the entire duration of the program. That would be the case, for example, if you return to the reference to the standard library constant pi is valid for the entire duration of the program. Where it gets more tricky, however, is when you have a function that takes multiple references as inputs and returns at least one reference as output. Because in this case, the compiler doesn't know what you're trying to do. Should this function be allowed to return output that comes from X, from Y, from both? This affects the API because in Rust, you can only use valid references, which means that the compiler must be able to track when you call this function what you can do with the output reference. And it's not just a compiler matter, actually. Your users will want to do for how long they are able to use this reference. And that's why Rust has some special syntax called lifetime annotation, which is a special kind of genericity where you can say, I define a lifetime that I call, say, A, and I say, okay, this output reference actually has the lifetime of this input parameter. Lifetime annotations are a relatively tricky concept in practice. It takes a fair amount of time to learn how to use them properly. So my advice to you would be that as soon as you start running into the need for them and you are just a Rust beginner, you may probably want in the beginning to reconsider and just make copies of data instead of passing it by reference to avoid this difficult part of the language in the beginning. Then once you've gained more experience and feel more confident, you can start learning about this aspect of the language, which is extremely powerful and allows many interesting things like in-place parsing and that sort of stuff. And so assuming this chapter wrote as originally written, in which case it would be about squaring elements of an array, then you would have seen an improvement for small inputs due to reduction of memory allocation work. But my understanding is that I failed to rewrite this chapter as the rest of the course evolved, and that's why Mathieu did not see the performance benefits. Since that's a bit of a tricky concept, I would probably start answering questions now and then move on. So Mathieu, I'm not quite sure what happened here, but I suspect what happened is this is a course rewrite error where I initially wrote this chapter with a particular example in mind, and then I changed the rest of the course and forgot to rewrite this chapter. In that case, it's expected that you don't see anything. If actually this chapter is written correctly, and I did have you do the exercise on a squaring benchmark, then what may happen is that you have not tested it on small enough input to see the performance difference. Because the overhead of allocating is something you pay only once. So if you're allocating a vector and filling it with lots of square numbers which use lots of computations, you will not see the overhead of memory allocation. And then the benefit of in-place access will not be so apparent. So more questions, perhaps. Michael, so it transfers ownership for VEC, but it copies for arrays. Yes, exactly. VEC and array behave differently here, and the reason is that VEC manages a resource, a memory allocation, whereas arrays are just a bunch of bytes, and nothing special happens when you delete an array. But one thing to keep in mind is that when you move around an array and actually copy it, you are doing a deep copy. And this means that copying big arrays can be costly, and you want to avoid it in a loop, for example. So Mathieu, regarding moving and copying, so is that a typo, that example? Actually, here, it's not. The reason it's not a typo and you do get a compiler error in this case is that the moment you've taken the resources managed by V and you've moved them into V2, V does not have access to these resources anymore. Rust operates on a single ownership principle, unlike languages like Python or Java, where multiple variables can be owning a single memory resource. This means that as soon as you've moved the memory allocation of V into V2, V does not have access to this memory allocation anymore, and you cannot use it.
Yeah, wait, it's on the second one, not that one.
Yeah, the second one is just a translation of this example, but with arrays instead of vectors.
Yeah, but then you're printing A2.
Yeah. Oh, sorry. Yes, I see what you mean. Yeah,
That's
this
my
one need
point.
to fix.
Okay.
Sorry, I missed that. I will fix that one. Copy and paste errors are a pain. Meanwhile, so yeah, the intent here was to read from A, and this you can do with arrays. Okay, Sergey, does the assignment operator return the assigned value as in C? No, it doesn't. The assignment operator in Rust returns the unit type, which you can think of as an empty tuple. That's the type that any operation which does not return a value returns in Rust. So like, for example, if you call print, it also returns the unit type. Assignment returns the unit type. Gregor asks, is the static global ref lazy? Will it exist on the stack if we don't use it at all? And this, I'm not sure if I fully understand the question. But to give an example here,
I can explain. The question is because in this we are referring to some consts, a variable from a library, and then if we don't reference this variable at all, will it be like instantiated on the stack or not? In the runtime, yeah? Yeah, if in
no,
the
it's in
runtime.
the it's not on the stack actually, it's on the global program segments in the binary.
Okay, so it will be in the globals.
Yeah.
Get it. Yeah, okay.
Yeah, basically when you see static in Rust, you can understand it as a synonym for global in other programs, in other programming languages. It
Okay,
has
thanks.
also this meaning in C++ sometimes, but it may also take other meanings, which makes it a bit confusing. And so the question of, are we still working with the Summit benchmark? That was the intent, but I think I failed to correct the chapter text. I do need to check this after the course and fix it. But yeah, the intent was to work on a floating point sum benchmark. And I may need to introduce a different benchmark to show the ownership effects then. Next question. Can you explain again how fn once is able to enforce the function being called only once? So fn mute, and fn once, the way they work is that in order to call a function via the fn trait, you need a function or a function-like object, like a closure, using the fn trait. You need only to have a shared reference to the original object. In order to call it via the fn mute trait, you need to have a mutable reference to the object, to the function object. And in order to call it with the fn once trait, you need to have an own value. And then because the compiler ensures that once own values have been moved somewhere else, they cannot be used anymore, this transparently enforces the desired property of being able to call the function only once. To become more fluent in Rust, are we supposed to know how variables manage their data by reading the source code, perhaps? So actually, when you look at the documentation of a type, one thing you can easily get in Rust documentation, and can show you that, is which traits these functions implement. I really need to know why my web requests are so slow this week. And when you look at a particular type in the standard library documentation, for example, on the sidebar, you first see a list of methods. You see that vec behaves like the equivalent slice, so you can use all slice methods as well. And then you see a list of trait implementations. And what you want to look for here is whether the type implements the copy trait or not. The copy trait indicates that a type does not manage any resource and may be copied bitwise without losing access to the original value. So here you can see that for vec, we have clone, we have debug, but we do not have copies, so we cannot do that. Whereas if I looked at array, I would see that it does implement copies, and more precisely, it implements copies if the element type implements copies. So By checking the documentation, you will be able to easily find out whether a type has a copy or move semantics on assignment.
So just to follow up, so if there is a copy trait, basically it's going to be on the stack.
Well, it's more of a question of what happens when you do this kind of A equal B pattern, you know.
I see. So if there is a copy, if you do A equal to B, you can create as many independent
You can create as many
copies.
copies as you want just by assignment.
I see. Thank
if
you.
it's copy. Whereas if it does not implement copy, then assignment moves, and once you assign, you cannot use the original value anymore.
So if there's no copy, it's going to be moved. If there is copy, you can create as many copies as you want.
Yeah, that's it.
And if it can create copy as many as you want, but you have to call the copy routine, right? If you are doing A equal B, it will still be a move, right?
If you create A equal B, it will still be a move. So if you write let A equal B, and then you want to use B again, it depends whether the type of B implements the copy trait or not. If it implements the copy trait, you're fine. You can create as many copies as you want.
Oh.
If it does not implement the copy trait, then that's considered as a move, and then you cannot use the original B value anymore.
Okay, so it means that the copy trait is called behind your back, I would say. So as soon as you were referencing the B variable later, then it means that the compiler will put a copy there.
Yeah, exactly. If you don't use
Okay.
the B variable afterwards, the compiler will just, the naive implementation of a move in Rust is a memcopy,
Okay.
but the compiler is smart enough to not perform the memcopy if it sees that you are not using the original value after that.
Got it. Okay. Thanks a lot.
If the sum function in the benchmark will be only once, will it transfer the reference cheaply into the benchmark? I'm not sure if I follow, but I see that you kind of replied to yourself afterwards, so maybe that's not a question anymore.
Yeah, probably I got it wrong, so never mind.
Okay. If it comes back later, feel free to ask it again and we'll discuss it at that time. It's a bit of a subtle concept, this ownership borrowing thing. That's why I introduced it relatively late in the course, so that you can first get exposed to the easy parts of the language before we can move on to more advanced things. So if there are no other questions here, I will move on then, as fast as my network connection will allow me. So we do have performance problems that we need to take care of, however. One thing that you would be able to tell if you looked at the assembly of our original floating point sum is that it does not use the SIMD instruction from the CPU, which allow you to do multiple floating point additions in a single CPU instruction. And people are usually quite angry about that, but it's good, to put yourself a bit in the shoes of the compiler also and know why that's not done by default. The problem is SIMD first is very hard for compilers because these are very special purpose instructions that only work for specific data types, for if you have enough data of that type, if you if the data is suitably aligned in memory, if the data is contiguous, and so on. It's sensitive to many low-level details that people are not usually trained to think about at all times. And the problem is compilers optimize code by going step by step from a naive translation of what you wrote to an optimized version. And in case of SIMD, you need, as a compiler, to take many seemingly useless steps before you are able to apply the SIMD optimization that will suddenly give you a big performance benefit. So that's the first reason why compilers have a hard time with SIMD. It is that SIMD only works in corner cases, and it may not be obvious to the sophisticated graph theory problem that a compiler ultimately is, that there is a path that will take you to the SIMD direction. But the second problem is that compilers, when they optimize code, always operate under a golden rule, which is that optimizations are not allowed to change the results of a program, the bitwise results. So there are some nuances to that rule. Some compilers have a special relaxed mode where they allow themselves to change the floating point results. Some compilers just don't care because they are made by hardware vendors like Intel, and they care about benchmark numbers more than reproducibility. There's some nuance here, but in many languages, by default, compilers are not allowed to transform the code in such a fashion that the speed of execution changes. And the problem is, if we look at what we wrote, and we said, okay, we want to iterate and then sum, and the way sum is implemented in Rust is that you start by initializing an accumulator to the neutral element of addition. Then you iterate over the elements of the input iterator. And then you add these elements one by one to your accumulator. And actually, there's a typo here. I will have to fix it later on. But anyway, this can only be done at the hardware level by taking the accumulator, adding the first number, adding the second number to that result, adding the third number to that result, and so on. If you do it any other way, the floating point rounding will occur in different places and the result will be different, which for some computations can have catastrophic consequences. Think Kahan summation, for example, which allows you to get double precision results with single precision mathematics. And the problem is, if we actually wanted to use our SIMD hardware properly, what we would actually need to do is more something along the lines of that code. So we would need to first have so we would need to set up not one accumulator, but n accumulator, one per SIMD lane. That's a hardware concept, which is basically how many floating point numbers here you can process in one instruction. Then you would need to iterate over chunks of the input that have the same size. Keep in mind that the remainder needs to be handled differently. Then iterating over these chunks, you would need to jointly iterate over the n accumulators and the n elements of the chunk of matching length and add one element to each accumulator. And this can be compiled into SIMD code, right? Because here you are basically taking the first 8 elements, adding them to your 8 accumulators, the next 8 elements, adding them to your 8 accumulators. So you're manipulating floating point numbers in chunks of 8 elements, and that can be translated to good SIMD code. And then afterwards, you will realize that your input has a size that may not be a multiple of the hardware SIMD width. So you will need to do something special with the remaining elements, typically involving some Scala code. And then you will need to sum all your working accumulators to get the final Scala result. And the problem is compilers are not allowed to go from here to there without changing the result. So what do we do then? Well, one thing that's on the horizon for Rust, it's not yet in the stable release of the compiler, but I wanted to showcase it here because it's so much more convenient than the existing stable versions, is we have hardware agnostic SIMD primitives. So why do we need that? Well, the problem is there is actually not one set of SIMD instruction in hardware. Intel and AMD alone, which are the most common CPU manufacturers, have released more than 35 SIMD extensions to their instruction set in around 40 years of history. So you get, if you computed a bit of an abusive average, you get one new SIMD extension per year. And if you wanted to write code that runs perfectly on every x86 CPU from the dawn of time, you would like to review all of these extensions one by year of introduction and check if your code compiles well, assuming only those extensions are available or not. Meanwhile, ARM so far managed to remain relatively consistent since their switch to 64-bit with Neon. However, they recently decided to bless us with even more of a mess in the form of the scalable vector extension, which means that now, when you're programming for ARM CPUs, you need to handle two ways of handling SIMD, which are completely different, have completely unrelated logic, and the code that uses it is completely, you need to rewrite your code completely for that. And given how they designed that, you can expect that for many years to come, we will have ARM CPUs that only support one way of doing SIMD and ARM CPUs that only support another way of doing SIMD. It's not like, use sufficiently recent CPUs and it will solve the problem. No, it will remain a problem for many generations to come. And here we are just considering two CPU vendors. Sometimes people want to also work on weird embedded architectures, IBM Power, and so on. And that's even more SIMD instruction sets to consider, each with their own logic. And what STD SIMD proposes to offer you, combined with a third-party crate called Motivation, is that you should be able to just say, okay, I want my code to be compiled for these hardware configurations. And then you need a bit of black magic to translate this hardware configuration into SIMD width. That's not so nice. I hope it will be improved later on. And finally, what you will be doing is you take your input array, you split it in 3 parts. So that's something I forgot to mention earlier is for optimal SIMD performance, you also need to manage alignment. You want, basically, if you use 250-bit SIMD, 256-bit SIMD, you want to have a starting address that's a multiple of 256-bit or 32 bytes. And so this basically splits your original dataset into 2 scalar parts called the peel and the tail that are not properly aligned, and 1 middle part that is correctly aligned and composed of SIMD vectors, where you have a SIMD vector type that looks like this. You say, I have a SIMD vector type. It contains 32-bit floating point data, and it has this many lanes, as recommended for this hardware configuration. And then finally, you do the scalar sum of the unaligned part because SIMD will perform terribly for it. And you combine the sum of the SIMD results with the scalar sum to get the final scalar result. So I will not claim that this looks good. What I will claim is that it looks better than this. And it's more general purpose because you can use something that looks more like explicit SIMD instructions, and that has better odds of being correctly compiled into hardware SIMD instructions. Now, again, that's a bit of a future compiler feature. Right now, you need to use a nightly compiler release to use it. So assuming you are a person who targets stable versions of the Rust compilers, what are your alternatives? I would mention 2. One is called Slipstream. And basically what this one does is it does the equivalent of this under the hood. So it writes code in such a way that the compiler has a better chance of translating it to SIMD code automatically. It's not perfect. Usually you get a slowdown of a factor of 2-3 with respect to peak hardware performance, but it's available today, which is nice. And another library which I would recommend is SafeArch, which tries to make manual x86 SIMD programming a bit more tractable to normal human beings. By which I mean that, you know, when you are doing, did I mess up my link? Yes, I messed up my link, perfect. So if you go to the proper place, you can get instructions that have names that normal people can read, which is much unlike what you would get if you used the actual Intel hardware instruction names, which you can find on the official Intel Intrinsics guide. Oopla, what's that? And once Firefox will be done being slow, basically what I'm trying to say is that Intel will give you instruction names that look like this. And here you get names that look like this, and I will let you decide which ones you prefer. So that's still x86 specific. It's still basically writing higher level assembly, but at least it's peak performance, unlike Slipstream, and it's not as bad as direct hardware intrinsics. So questions, those lifetime has to be a no. You can name lifetimes however you want. My advice would be for many code to name lifetimes like the variable that you're borrowing from, because that's one possible choice. And when you can use this choice, it results in clearer code. But here I use A as an example that, you know, you can name your lifetimes however you want. And it's for simple purposes, simple single letter names work, right? So Rust is different from C++ in the sense that it will prevent accidental copies on assignment. Yes and no. For most types, it will prevent it because most types are only movable. They do not implement the copy trait. However, for types that do implement the copy trait, then you will get the deep copy, which can be a performance issue. Some people are unhappy about this state of affair. There are some ongoing discussion about maybe we would like in a future edition of the language to make copy of large objects also a compiler warning, but then we need to define, you know, what constitutes a large object, and that's where programming language design can end up getting a bit messy, you know, when this sort of fine-grained decisions need to be taken. I will not answer questions about the chapter 12 yet, because I have other chapters to cover first. Can we recognize which CPU we have at runtime and switch the standard library to the right SIMD at runtime? Yes, that's what this does, in fact. So this multivariation crate allows you to say, okay, I want to compile versions of my code for this architecture, this architecture, this architecture. And then at runtime, when you call that function, it will result in some form of dynamic dispatch where the first time you call the function, the architecture will be detected, and then you will dispatch to optimize code for the actual CPU. Okay, let's move on. I see maybe there are a few messages in the chat. Let me check. Yes, indeed. I keep tripping Python references up. Yeah, such a mess. Anyway, and yeah, RISC-V is even more fun. And you know, some people think it's the future, so maybe we'll need to deal with it someday. Is there a way to disable the copy trait of arrays? Actually, yes. The copy trait is opt-in for types that you define. When you define a struct, by default, the copy trait is not implemented, even if it could be implemented because of the struct contents. And you may or may not choose then to implement the copy trait. The reason why that is the case is encapsulation. When you have some kind of abstract type, you may not want to commit to implementing the copy trait because this restricts your implementation later on. So indeed, if you wanted to have arrays that don't implement the copy trait, you would just have to have a struct that wraps an array for which you do not implement copy, and that would solve it. So let's move on because we have a few more hardware features to cover. So I have covered SIMD. Now we need to cover superscalar processing, which is the ability of CPUs to process multiple instructions per clock cycle. And actually, we get here similar issues as with SIMD, where in order to correctly leverage superscalar execution, our code needs to exhibit a sufficient amount of instruction level parallelism. And in a reduction context, like summing floating point numbers, for example, this means that we should have several different accumulators. And here I give you a scalar example, but you must imagine that in the real world, we would need to have multiple SIMD accumulators. And the problem would likely be obvious to those who implemented this sort of implementation before. It's that you need to write 3 copies of your code if you want ILP of 3, or a 4th copy because your number of elements may not be a multiple of the number of accumulators. And then, you know, anytime you need to change the code, you must modify all the copies. And for many years, that was the only way to do it. I have been working on a better option in Rust. It's a bit experimental, as you will see throughout this course. It has more edge cases than I would like right now. But the gist of the idea is that you can have your iterator pipeline. You do, unfortunately, if you have an iterator of references, need to turn it into an iterator of values via methods like copies or clone. But once you've done that, you are able to say, I want to do a sum with 3 parallel instruction streams. And this will generate the equivalent of this loop without requiring you to write it with n copies of your code. And the idea is that this should work in my dreams again for any iterator pipelines. Like, for example, if you wanted to compute the square norm of some vector, then you would be able to do a kind of modified version of the iterator fold that allows you to take elements and do fuse, multiply, add with elements and accumulators, and then at the end sum the different accumulators all without you having to rewrite all this mess. Again, it's a bit young, but I'm a bit happy about it anyway. Questions? No questions so far. Okay, let's move on then. And finally, we have parallelism. So here there is a quote I really like. Unfortunately, I do not know who originally wrote it. It's one of these quotes that gets thrown around a lot, so I'm not sure who is the original author. But anyway, you can have a second computer once you know how to use the first one. And this was, I think, originally said in the context of distributed systems, but personally, I think it perfectly applies in the context of local parallelism with threads as well. You should not attempt to implement multi-threading in your program until you have already a version that makes correct use of a single thread, because then you're kind of wasting execution resources that could have been used by other better implemented programs, right? But let's say that now we have very fast sequential code. So how do we do multi-threading? The easiest way in Rust is to use a library that's called Rayon. The general idea of Rayon is to provide you with parallel versions of all the iterators that you have in the standard library, but with iterators and iterators methods, so that you can do things like, I take my vector of floating points number, I turn it to a parallel iterator, I sum it, and it does the moral equivalent of splitting it into one subset per CPU core, doing the sum and reducing at the end. It's super convenient. You can tune how many threads you are using with the Rayon numthread environment variable. It's much like OpenMP. But as soon as you want to do more complicated pipelines with operators like map or filter, you may wonder, okay, but how do I prevent race conditions? And the answer is the language prevents race conditions for you. Because we have this principle in Rust that data is either shared in read-only mode or has exclusive mutable access, we cannot get data races bugs in Rust, which are the worst kind of parallelism bug where your parallel program basically turns into undefined behavior. We do still have parallelism bugs, however, we can still have deadlocks, race conditions, and so on. We still need to apply proper patterns to avoid these, but we avoid the worst kind of bugs, the bugs that are hard to debug, that have differing effects depending on which compiler you are using, and so on. Now, if you try to use Rayon, as discussed earlier, for tasks like floating point summation, you may realize that, unfortunately, the library is not tuned perfectly for this application. What happens is that your floating point sum is the Rayon runtime will slice it into chunks, and as long as it has available CPU cores, it will slice it into smaller and smaller chunks to keep these CPU cores fed. And unfortunately, this will result in very inefficient synchronization patterns at the end of iteration if your parallel operations are very fine-grained. And the way we can resolve this is by giving Rayon some limits, saying, okay, I only want you to slice my input data down to chunks of a certain size, and at the end, I'm going to take things in my hand and implement my sequential computation the efficient way. And this means then that I can use all the things we learned in previous chapter to use our efficient sequential sum on each core. Another thing that you will realize is that Rayon has a bit of overhead for starting parallel execution and waiting for it to complete. And the way you will need to resolve this, if you care about performance on small data sets, is by having some kind of sequential path in your program. Like, you will want to say, okay, if my that input data is smaller than a certain amount, then instead of calling the parallel version, I will call the sequential version directly without going through the overhead of spawning and joining threads. Given these two precautions, Rayon is actually surprisingly usable for HPC purposes. Its main limitation today is that it does not handle non-uniform memory access very well. So if you're using Rayon for parallelism, you will probably want to either set up one Rayon thread pool per NUMA node, or to just, do what almost everyone does and spawn one process per NUME node and communicate via MPI. Now I can answer that question. So why do we use the Rayon crate rather than another one like Flume or Tokyo? I don't remember about Flume specifically, but the main design goal of Tokyo is to allow you to execute asynchronous I/O workloads. It's not mainly designed for compute. And it means that with Tokyo, you will not get this sort of nice primitives where you can just take a collection, iterate over it in parallel, and so on. So one first reason is Rayon is a lot more convenient to use for this sort of use cases. And another reason is that Rayon is also better tuned for this sort of problems. Like Tokyo has some rules like you should not run long-running tasks on the async thread pool. And these rules make sense in the context of IO-bound programs like web servers, but not so much in the context of compute-bound programs like what we're doing here. Any other question here? If not, I will move to my last building block before we can go to a more sophisticated problem. And that building block is ND array. So, so far we have been studying vector operations. We have been studying the parts of Rust that you need to know in order to implement all the classic one-dimensional computations, FFT, BLAST level 1, and so on. Unfortunately, in the real world, people think that multidimensional problems are important and worth solving. In fact, so I've been told during my university classes that most useful physics and chemistry problems are multidimensional, which means that we will need to have some way to handle multidimensional data. We could handle multidimensional data like people did in BASIC in the 80s by having one-dimensional array and using sophisticated tricks to convert multidimensional indices into one-dimensional indices that we will then use to index into this one-dimensional array. There are only two problems with that. First of all, if you have ever written this kind of code where you do lots of these manual indexing operations, you will find out that it's an extremely error-prone way to write programs. You will get this wrong over and over again. You will use the wrong length here. You will use the wrong index component here over and over again everywhere in your program. End up with the transposition of your matrix instead of the matrix you want in the best case and complete rubbish in the other cases. And then there is another problem which is more specific to Rust, which is that when you start doing lots of 1D indexing like this, you will run into the usual issues of indexing in Rust, which is that you can get the index wrong as in any other language, so that will cause crashes. And even if you get the index right, the overhead of checking that the index is right at runtime will cost too much in many cases. This is why we have the ND array external library. We call these crates in Rust, which resolves all of this problem by implementing all this complicated linearization code for you and providing you with multidimensional equivalent of Rust vectors and slices, so that then you can manipulate multidimensional arrays like you would manipulate one-dimensional arrays with all the iterator, comfort, chunking, windows, and so on. It's not the only library that tries to do this, but it's certainly the most popular one at the moment. And it's also one of the most general purpose ones. in the sense that many other libraries, try to solve one specific problem like linear algebra and so on. NDArray tries to provide you with a general purpose multidimensional array abstraction that you can use for anything like Fortran arrays. And it's quite well implemented. As you will see later, you can run into some performance edge case, but it's not that frequent. And I find that overall, it provides today the best trade-off between ease of use, runtime performance, generality, and expressive power. As always, adding a new dependency in Rust is very easy as long as it's a Rust-only dependency that does not dependency code. You just do cargo add NDArray, and then on your next build, the dependency will be automatically downloaded and built. One thing I would like to point out for this specific dependency is that it has many optional features. Things like approximate comparisons, ability to use your BLAS implementation for linear algebra operations, ability to perform matrix multiplication in parallel, even if you don't do explicit parallelism in your code, some nice tricks for interoperating with Rayon and so on. By default, all of these are disabled except for the STD feature, which allows you to use the parts of the library that depend on having an operating system, like memory allocation. The idea here is that if you don't need this feature, you shouldn't spend precious compilation time compiling them, and that will cost compilation time, overhead. It may make your binary bigger if the compiler does not manage to delete the unused code. So if you don't need it, you probably don't want to add it. But yeah, you may need some of these later on, so keep that in mind. So once we have NDArray in your program, what does it look like? So the heart of NDArray is a type that is called ArrayBase, which is a very generic multidimensional array type. By very generic, I mean that the inner array can have any dimensionality. It can be 1D, 2D, 3D, 4D, anything. The array base type may either own its data, like a vec, or it may be borrowed from another array, like a slice. And that's really powerful, but when you are learning Rust, you probably don't want to deal with the signature of this type, which, because it's very general purpose, very generic, it gets a bit tricky, right? You're templated by dimensionality and some data container. You need to check what are the implementations of the data container. You get a bit into the internal library. That's not so nice. This is why you have some nice user-facing aliases that allow you, in common cases, to get like a 2D own array, similar to vec or NumPy NDArray, 2D read-only view that's similar to a slice of a 1D array, or a mutable view that's similar to a mutable slice versus a shared slice before. And actually, when you look into it, these are just aliases of the array type in some spatial configuration. But because they are just aliases, unfortunately, the documentation generator that the NDArray project uses will not show you all methods when you show the alias. You will need to get into ArrayBase to get all the methods. And that's why I'm telling you that you will want, in most cases, to keep the ArrayBase documentation close by, because that's where almost all the methods are described. There is another interesting tool in NDArray, which is the array macro. And its purpose is to let you create multidimensional array in a fashion that's similar to creating single-dimensional vectors. That's not the only way to create arrays. It would be a bit limiting. You can also create it by specifying the shape of your array and mapping from index to value. And you can turn vecs into multidimensional arrays and so on and so on. Once you do have a multidimensional array, an array, you will want to iterate over it. And then you will run into the fact that, unfortunately, ND array does not directly use standard Rust iterators. It uses its own abstraction, which is something that's called an ND producer that can be converted to an iterator, but provides additional information with respect to a standard iterator, like it knows about notions like data ordering, data contiguity, contiguous, non-contiguous dimensions, sparse views, dense views, and so on. And this allows it to do some things more efficiently than a standard iterator would. Sufficient to say, for simple use cases, you will probably just want to take these and convert them to standard iterators. But for more advanced cases, you may want to study the ND-array specific API, as it may be more efficient for what you want to do in some cases. Let's give you an example. So here I'm creating a multidimensional array, and I'm iterating over 3x3 windows. And as you can see, this generates an ND producer, but because for loops do an implicit conversion to iterator, it actually works. And if I run this code, I would first get the window composed of these elements, then the window composed of these elements, then the window composed of these elements, and so on. There are many producers in ND arrays. Some are more specialized than others. They target more specific use cases, and it means that they can apply more aggressive optimizations. So it's often a good idea to spend some time looking through the various options that you have at your disposal to solve a particular problem with ND array in order to find the producer that's most specific to your use case and likely to be most performant. You can index multidimensional arrays. The main difference is that you pass in arrays or tuples of indices instead of passing individual indices. On the other hand, unfortunately, there has been a little oversight in the design of the Rust indexing operator that cannot be changed without breaking compatibility with thousands of lines of code, which means that for slicing, you will need to use this slightly gory custom syntax. It's a bit weird, but you'll get used to it. Slice is only one method. It produces a read-only slice that you can share. It's analogous to doing &vec with a start and finish. You have other slices. You can do mutable slices. You can create multiple mutable slices at the same time, which is a good way to avoid the limitations that come from the fact that in Rust you can only borrow one mutable slice from an array at a time. Here, basically, ND array does some check to make sure that you're only accessing disjoint indices. And if so, it uses unsafe code to bypass this limitation, which in this case makes no sense because you're not creating mutable references to the same elements. And you can move data, obviously. Questions. Can you speak a bit about the combination of parallelization, SIMD, ILP, and potential trade-offs? Well, the way this course is originally designed, we just implement one after the other. And what you will see if you do run benchmarks for many input sizes, as I advise, is that the more you optimize the large input case, the more you will pessimize the small input case. Sometimes you can work around this using the trick that I showed you in the context of Rayon, which is to put some cutoff below which you switch to a simpler implementation. But you will not always be able to use this kind of trick. And even the check for very small inputs has some impact. Also, if you end up having one implementation for input from size 0 to 10, then one implementation from size 10 to 100, then one implementation from size from 100 to 1000, then one implementation from size, you get the idea. You will get a bigger and bigger program, which can be harder to maintain and which will take more time to compile and consume more memory, be bigger in the end, and so on. So overall, the idea is that you only want to apply all these implementations when your input is very large, all these optimizations when the input is very large. If your input is smaller, what you most likely want to do is to apply them in the order that I suggested. First, you try to apply SIMD, see if it helps at your input size. Then, if it helps, you can try to also add some instruction level parallelism, which tends to help at even larger input sizes. And finally, you can start thinking about parallelism. And I do not cover distributed computing in this course, but that would be the next step as well. When we use Cargo and RustUp, does it always install to a base environment, or can we create virtual environment like Python? So actually, Rust does not need virtual environments as much as Python does, because Rust uses static linking for everything, almost everything, except linking to external C libraries, or if you specifically direct it to use dynamic linking. And what this means is that Cargo is able to have completely isolated build environments for each of your projects. And you cannot get collisions where you have multiple versions of a library installed that are incompatible with one another, for example. This kind of issue you can only get when you have native dependencies like HDF5, FFTW, and so on. And then the best way to handle that is via the environment management mechanism that are provided by the mechanism that you use to install those C libraries. Like, for example, I would highly recommend SPAC for C dependencies for building and installing them. It's done wonder for me. It's a really nice package manager that can manage C, C++, Python dependencies, even Rust ones these days. And it can build the entire stack like Cargo is able to, and it can manage isolated virtual environment where your projects do not interact with each other. But if you're not interacting with any C code, which I wish to you because these always cause trouble, but sometimes you have no choice, then you don't need an extra environment management mechanism because Rust on its own manages build environments very well. All right, so we are almost at the end of today's lecture, but let's take a peek into tomorrow and look into the Gray-Scott model that we will be focusing our attention on in the next day. So let me share my slides first. That should work. Yes. So, Gray-Scott. Let's recap. So far, we've introduced Rust for numerical computing. We've seen why I consider C++ to be its primary competition among the various languages that are mainly used today for numerical computing. And I hope I've given you enough comparison points to see how Rust and C++ differ at this task. I also gave you, I hope, all the Rust basics that you will need for everyday numerical work, small-scale work, like from declaring variables to basic computations like dot products. And that's not bad, but I mean, if you're not the kind of person that's easily convinced, I will understand, because I mean, yeah, we do already have very good dot implementations, FFTW implementations, and so on. We don't really need Rust for this, right? We're not rewriting these operations every day. So a more interesting question perhaps is, how would Rust scale up when we start moving on to more realistic computations? And this is why we introduce Grayscott, but not this Grayscott, which unfortunately I've discovered you will find if you search for Grayscott on the web. Now, rather, I'm talking about the Grayscott reaction diffusion model. The basic idea here is that we are taking a simple model of chemistry where we basically treat chemistry as a cellular automaton. We say, okay, we have species, chemical species U and V, and if we end up having one species U that is surrounded by two species V, then this species U will be transformed into species V. So again, like a cellular automaton, the game of life, however you call it. That's not enough to get some sustained chemical reaction. To see some more interesting effects, we also need to add a source term that adds more of the U species to the simulation domain. Otherwise, this reaction will deplete U over time and will run out of it. And we need a drain term that removes some of the V products. Otherwise, we'll just drown in that product, you know. Technically, that term does not remove the V species. It turns it into a non-reactive species P in the original Grayscott model. But since that species does not chemically react with any other species, we did not bother in the Grayscott cool simulating it. And finally, for a bit more realism, you also want to have diffusion term for species U and V, because nature does not like, you know, having inhomogeneous concentration of chemical species in space. It wants to smooth out the concentration of U and V. And furthermore, here I presented you this problem as a discrete problem where we would simulate individual atoms or molecules of U and V. For real-world chemistry, that's not practical because we are commonly manipulating numbers of elements in the order of magnitude of the Avogadro number, which is huge, and the computers can't handle that much data. So instead, we are going to the continuum limit, and this will mean that we will have some differential equations with the output, so to say, being the derivative of the concentration of U and V species at any point in space. Here you see the reaction terms, which destroys U and creates V at a rate that's proportional to the product of the concentration of U and the square of the concentration of V, which you can think of as the concentration of pairs of V. We have source terms that add more U species. They are a bit more complicated than the previous slide would suggest, but it's just a matter of making the system a bit more stable over simulation time. And then we have the diffusion term, which uses the Laplacian operator, which is, if you do not know what that is, just know that this is a kind of spatial derivative that's high when you are surrounded by concentrations that are higher than yourself, and that's negative and low when that's negative with high magnitude when you're surrounded by lower concentration. So it tends to smooth out concentration over time. And then we have this nice equation, and the question is, how do we solve for U and T and V and T, which is what we want in chemistry and physics? And you go ask your mathematician and he says, I don't know. What, you don't know? No, I don't know. Basically, all these differential equations that couple time derivatives and spatial derivatives have turned out to be very hard for mathematicians. They remain an open problem in mathematics. I think for one particular one, the Navier-Stokes equation, there is $1 million prize to the first person who will find an analytical solution to it. What do we do then? Well, we turn to the dark side of mathematics, the numerical analysis, which says, hey, yeah, we cannot compute the exact result, but it's okay if it's an approximation, right? And because this is a programming course, not a numerical computing course, we will use the simplest numerical computing scheme that could possibly work. That means that we will discretize our space in a finite different schemes. So we will consider a regular grid in space, and for simplicity, we will consider a two-dimensional space because that's easier to visualize by eye. We will only compute concentrations of U and V on the points of this regular grid. And I forgot to mention also that we will limit the extent of this grid. And once we have achieved this, then we will say that the spatial derivative is approximately the difference of grid neighbors divided by grid steps. That's a bit hand-waving because I didn't want to put the full gradient Laplacian formula here, but you get the idea. And for time, we will do something similar. For time discretization, we call that Euler's integration method. And the general idea is we say that U after some time delta t has elapsed is equal to the U before the time elapsed, multiplying by the time interval and the derivative at the initial point in time. Our main goal here will be to produce nice pictures. More precisely, the idea is that we will save the precise data into an HDF5 data cube like a good numerical scientist would. But because this data cube is a bit hard to manipulate, we will then post-process it into nice-looking images. And the way we are going to do that is that actually one of the dimensions of this cube is time. And we will produce, we will slice our cube over this time dimension. And for each time step, we will produce a PNG that visually represents the corresponding chemical species concentration. Along the way, we will also try to follow some good software engineering and UI design principles. So we will want some simulation parameters to be tunable using command line arguments. We want to report progress as the simulation moves forward so that users can get an intuition of how fast or slow the simulation is. And because this is a numerical computing course, we will also want to get as close as possible to the peak performance that our CPU is capable of. Well, that last slide was not written correctly for the circumstances of today, but I hope you get the idea. I can answer some last question and then we will have to conclude. Someone already said that. All right, if there are no other questions, then see you tomorrow and we will see how Rust looks like when we try to apply it to this sort of more sophisticated physical-chemical simulation.